Hey Ramblers, now that we've covered chapter 1.1 and we've talked about linear functions, we want to step into something a little more complex, and that's going to be exponential functions. Those are covered in chapter 1.2. Now they're not terribly difficult, but they are different than linear functions. So at first we're going to cover any misconceptions that you might have about exponential functions, so we don't confuse it with some other things before we even get started. But then we'll talk about what an exponential function is and how do we recognize it when we're looking at a table of values or when we're looking at a graph. Then we'll talk about the general formula for an exponential function, and so what the different pieces of the formula do. We'll then look at a concept of concavity and what that is and how it applies certainly to exponential functions, but we're going to be using concavity to describe functions all year long. Okay, lastly, we'll talk about two concepts that deal really specifically with exponential functions. The first one is going to be this idea of doubling time or half time. The second one will be the most common function we'll look at, or the most common exponential function we'll look at this year, which is y equals e to the x. Now that may bring back some really bad memories from pre-calculus, but trust me, you're going to really like it in calculus. One of the reasons it's so common is a lot of the numbers and a lot of the functions that we work with are much easier to work with when they're expressed as e, especially exponential functions. Okay, so thanks for watching. Please pause often, take good notes, and I hope this helps.
There's really only one misconception I want to clear up, and that kind of comes from what is an exponential function. And many people look at something like y equals x squared or y equals x to the 10th and think that's an exponential function. But these, in fact, are power functions. Now, the difference is that in a power function, the variable is in the base. So we contrast that to an exponential function. Here, let's take, for example, y equals 2 to the x, or if you want, y equals 10 to the x. Here, this is an exponential function, and you'll see that the variable is in the exponent, hence the name. So let's be clear going forward not to confuse power functions with exponential functions. They're really both very different. Okay, in this book, the general form of an exponential function is given as p equals p naught a to the t. Now, what is each one of these? Well, p here, that's just our output. Okay. P naught, however, is the initial value. So, I don't know, let's say we're talking about bacteria. P naught would be the amount of bacteria that were in the petri dish when we started. Or if we're talking about money in a banking account, P naught would be the amount of money you started with. But A is the really interesting number. That's the growth factor. That is the factor that changes P as T changes. Now, A, when greater than 1, means that we have exponential growth. When A is greater than 0 and less than 1, we have exponential decay. Oops, exponential growth and exponential decay. Okay, let's move on and take a look at concavity, half-life, and doubling time.
The first thing we want to talk about when we talk about exponential functions is how to recognize them when we see them either in a table or on a graph. Well, the good news is they're really recognizable. Let's take a look at this population growth. It's the population of an African country, Burkina Faso. And you can see, if you look in the column on the not the far left, but the population in millions, that in 2003 it grew from 12.853 million up until the 2009 when it was 15.737 million. That entire time it was growing. So this next column over to the right, they calculated for us what the change in population was. And as you can see, that change is growing. So the change from 2003 to 2004 was 0.437 million, or that's about 437,000. But if we look farther down, you can see that that growth increases 0.457, 0.478, all the way up to 0.523. So this is clearly not a linear function. The change is not like slope. It's not constant every time. Now, at first glance, you might not even be able to recognize it at all. But let's do something with your calculator. Pause the video if you would, and please take a second to divide the value for a year. Let's take 2005 for instance. Divide 13.727 by 13.290. And then go on. Take any other values. How about the value for 2007 divided by the value for 2006? And each time you do it, you'll see that you get the same ratio from one year to the year prior. And that should always be 1.034. So take a minute and check it out on the calculator.
I love it.
Hi, can I get you two a drink?
You sure can, sweetheart. Johnny Red Neat, okay?
Okay.
Do it. Do it.
All right. And you?
Do it. Bacardi and cola, do it. Do it.
Okay, I'll be right back.
So that constant ratio in the change from one year to the next, be it roughly 1.034, 1.033, or close enough, that's the hallmark of an exponential function, is that the ratio from one value to the previous value is always the same. Okay, let's take a look at the graph and see how the graphs are also very distinctive as well. Okay, this is your basic exponential function, kind of in a very general form. As you can see, it kind of hugs along the x-axis before crossing the y-axis at 0, 1. Now, that 0, 1 is going to be if the value of p naught is 1, because that a to the t part of the function is going to equal 1 when t equals 0, because anything raised to the 0 power is 1. So the function hugs along the x-axis, then crosses at 0, 1, unless p naught is a different number, which will change that y-intercept, and then it grows. Now this function could certainly be reflected over the x-axis or reflected over the y-axis, and you learned how to do that in pre-calc. But just to give you a general idea of the shape, most of the exponentials we talk about will be in this kind of standard position, where it's hugging the x-axis in the negative side of the y-axis, and then rising as we move into the first quadrant. So let's take a look at this second picture here, where you see that you had, depending upon the value of the base, how close you become to the y-axis. When it's 10 to the x, you're very close to the y-axis. But as the base is smaller, like 2 to the x, you're a little bit farther away. It all depends on the base as to how close to the y-axis you're going to be. Thanks for watching. Okay, we talk about concavity now with exponential functions because lines don't have any concavity. Now, but I don't want you thinking that concavity only applies to exponential functions. Concavity applies to almost every single function except for lines and, well, I guess constant functions, but those are lines in a manner. So something is concave up if it is shaped like a smile. So if we look at example 1 here, example 2, these are both examples of concave up. So the function can be decreasing and concave up, or increase and concave up. We also have concave down is shaped like a frown. And there can be functions like in example 3 where it's increasing but concave down, or decreasing and concave down. These are really old terms to use as we try to describe functions verbally as we go through the year. Okay, let's take a look at this idea of half-life and doubling time in the next section. The last thing we have to talk about are exponential functions that involve e, because after all, this is by far the most common exponential function we'll work with in calculus, largely because the derivative of e, whatever that is very simple to calculate, and e's inverse operation is the natural log, which is also very helpful in calculus. So we better get used to seeing e and not being afraid of it. I would really like to call your attention down here to the first line here. These two equations can be equivalent. So p can equal p naught a to the t. We've said that throughout this video. Or you could write it as p equals p naught e to the kt. Now think about that. The two expressions on the right side are equal. So we're just replacing e to some exponent and having that be this equivalent to a. So we can rewrite anything in terms of e. Now, if it's exponential decay, we write it a little differently. For exponential decay, we start off with q naught times a to the t. Or if we want to write that in terms of e, we say q equals q naught e to the negative kt, where a is now equaling e to the negative k. So when we talk about exponential growth, this value of k, the exponent is positive for e. Exponential decay, the value is negative. You might recognize this from pre-calculus as PERT. You know, p equaled e to the rt, or p naught e to the rt. We will be doing a lot of work with this, and I'm sure this stuff will become a little more clear as we do exercises. Okay, Ramblers, thanks very much for watching.